Hello, this video is for Algebra 1, Chapter 2, Lesson 8. The title of the lesson is Applications of Proportions. The objectives for this lesson are to use proportions to solve problems involving geometric figures and use proportions and similar figures to measure objects indirectly. The vocabulary for this lesson is similar, corresponding sides, corresponding angles, indirect measurement, and scale factor. So why learn this? Well, proportions can be used to find the heights of tall objects, such as totem poles, that otherwise would be difficult to measure. So first we have similar figures showing up for our vocabulary, and similar figures have exactly the same shape, but not necessarily the same size. For instance, we could have two rectangles here, and I'll try to draw a couple rectangles here, and we'll go ahead and undo one piece there. There we go. Let's try to get it straight. Alrighty. And actually, I can make sure that these are similar because I'll just go ahead and copy them and duplicate them, and then drag that down here. Now I'll just resize it, and I think I can resize it. Oh, let's group it all together. There we go. I probably need to group it, and then I can resize it. There we go. So I now know for certain that these are two similar shapes because all corresponding angles are congruent. That means equal to one another, giving it the same shape. And I know that they are proportionate to one another because I scaled it down. So here I have two figures. They are not necessarily the same size, but they are indeed the same shape, both being rectangles. Now let's talk about corresponding sides. Corresponding sides of two figures are in the same relative position, and corresponding angles are in the same relative position. Two figures are similar if and only if the lengths of the corresponding sides are proportional and all pairs of corresponding angles have equal measurements. So that's why this is coming up in this lesson. We've been talking about proportions, and so we're going to look at whether sides are proportional in similar figures. Let's look at the next page here. First, reading math. Notice that AB with a line over it means segment AB. So for instance, over here I have this blue side of the triangle. It is indeed a line segment. It does have two endpoints, endpoint A and endpoint B. So it is a line segment. And if it has a line over the top of it, this means segment AB. We're actually talking about the line itself. However, if you have AB without the line over it, then this means the length of AB. So whenever we say AB here in our proportion that we have set up, we'll talk about that in a moment. But where it says AB, this is actually talking about the length of line segment AB. So these, this AB and DE, BC, EF, AC, F, DF, these are all actual numerical values that we have in here. Next, let's talk about over here that angle A, this little angle symbol here, we read that as angle A. It says angle A means angle A. If we stick an M in front of it, then we're talking about the actual measurement of angle A. So it becomes a numerical value at that point. So M angle A means the measurement of angle A. And we can see that in our illustration here. We're saying that the measurement of angle A is equal to the measurement of angle D. So angle A and angle D have the same measurements. So now that we've got the reading math and we understand that two letters such as AB and DE without a line over them, we're actually talking about the length of the line. And if we have an M in front of the angle, then we're talking about an actual numerical value, talking about the measurement of that angle. So in stating that two figures are similar, use the symbol, and this symbol here, it's called a tilde. And it sits on the upper left side of the keyboard, and to be exact, it's just above the tab button on the left side of the keyboard. For the triangles above, you can write triangle ABC is similar to triangle DEF. Make sure corresponding vertices are in the same order. it would be incorrect to write triangle ABC is similar to triangle EFD. And the reason for this is, notice that angle A, the A comes first, then therefore, since D is the corresponding angle, D should come first. Up here, we have the correct version of that. A is listed first, it corresponds with D, so D is listed first. B is listed second, its corresponding angle is E, so E is listed second. And finally, angle C, here the green angle, it corresponds with angle F, so F is listed last. So triangle ABC is similar to triangle DEF. And this right here that I'm highlighting, this is known as a similarity statement. I've kind of put it down here to highlight that. The text does not mention that. It's not really a geometry course, so we're kind of stepping over into the world of geometry and doing a little bit of geometry discussion in this lesson. So we'll just cover the needed points in this. But I do want to mention that this is a similarity statement. It is a statement that states that this triangle, ABC, is similar to triangle DEF. And since they're telling us so, we know that it's true. So let's see what it's talking about as far as these being similar figures, right? We can see they're definitely not the same size, but we do know that they are the same shape, or at least they appear to be. And we know that they are because they have congruent. Congruent means equal. So they have congruent angles. Angle A, red angle, angle B and E has a blue angle and a blue angle, letting us know that those are congruent. And angle C and angle F, you can see these are both in green, so they're letting us know that these angles are congruent as well. So we do have congruent angles. Now we just need to know, are the sides proportionate to one another? Well, notice that this side here, AB, notice that AB is listed first, and a little bit of highlighting might help see this. So notice that we have AB and DF, the first and second. So I know that AB corresponds with DE. I think I said DF a second ago. So AB is to DE as, and then let's go ahead and look at the next ones. BC and EF, we have BC and EF is our second ratio. And then finally, the last two, we're looking at AC, so the first and the last, along with DF. And we see that here, DF. So we kind of went through that, matching those up with the first two and the first two. And then we looked at the second and the third and the second and the third, putting those together. And then finally, we looked at matching up the first with the third and the first with the third. So this is where we find our angles, or we find our line segments to check and see if they are proportionate by setting up our proportions up here. And we find them by going through and matching up those segments using the similarity statement. And we'll do that some more. Let's go ahead and look at the next page. Finding missing measures in similar figures. Find the value of x in each diagram. So it's not necessary to do what I'm about to do. I'm just going to go ahead and set up similarity statements. So RS, and I want to go back to red. So RS matches up with BC. So we would have RS is to BC as, and then we have the second and the third, ST, is to CD. I'm drawing off because I should have made that a capital T. Uppercase and lowercase makes a difference here in geometry. And then R and T, RT, is to B and D, the first and the last, right? BD, first and the third, if you want to look at it that way. So I know that RS is to BC, as ST is to CD, as RT is to BD. Now let's see what it is that they give us. So we know that we have RT right here is 5, right? So 5 is to in BC. So BC is, how are they doing it? 5 is to, RT, yeah, I'm sorry, RT is to BD. So 12. So 5 is to 12, and we see that right here. And then we have RS is the first, and so it matches up with BC. So looking at BC, and we have 8 is to X. So 8 is to X. So whenever we do this, always, now you could do this as 8 is to 5. We could write this as 8 is to 5. And go 8 is to 5 as X is to 12. As X is to 12. And we would end up with 8 times 12 is equal to 5x, and we see that 8 times 12 is 96, and we end up with 5x, and we're going to end up with the exact same thing right here. So you could do it that way. However, I want to strongly encourage you to go ahead and get used to doing it of one figure to the other, and looking at this as 5 is to 12, the corresponding sides, RT, right here, is to BD, 5 is to 12, as 8 is to X, and 8 is RS, is to BC, okay? And if you do that, then you would end up with 5 is to 12, right here, as 8 is to X, and we would end up with this proportion right here at this point. So 5 times X is 5X, 12 times 8 is 96. Now let's go ahead and divide both sides by 5. The 5's would cancel each other, leaving us with just the X here. And 96 divided by 5 is 19.2. So the length of BC is 19.2. Let's look at the next one. Find the value of X in each diagram. Well, a few more sides here. A few more than what we have last. Triangle? Yeah, triangles. So here we have, notice that there's 1, 2, 3, 4, 5, 6 points on each figure. So we have 1, 2, 3, 4, 5, 6 points in each side of the similarity statement. So let's see, what do they give us? They give us GH. So they give us the first and the second, or the second and the third. So let's take second and third over here. So we know that GH is to NP, and and the other one is KL. So we got, no, JK right here, right? JK right here. So we're talking about QR. So as JK is to QR. And notice that my first value, both my numerators come from the first figure, and both my denominators come from the second figure. So GH is, and they notice they do it backwards on this one. They're doing NP is to GH, NP is to GH, and then they're saying RQ, which is the same as QR. So RQ is to KJ. KJ. And why they went backwards, I don't know. It's in the similarity statement, going left to right. It works out the same way, either way. Don't sweat it too much. But notice that I said GH, I said 4 is to NP. I'm saying 4 is to 6 as 2 is to X. So I'm saying 4 is to 6 as 2 is to X. And I would end up with 4X equals 12, divide both sides by 4, X equals 3. Now they're doing it a little bit different over here. So let's go ahead and look how they're doing it. They went kind of the opposite direction. They're working from, I work from left over to right. They're working from right over to left. Not that big a deal. So they're saying NP right here is to GH right here, as RQ right here is to KJ, is to this. So they're saying 6, is that right, 4? They're saying 6 is to 4 as X is to 2. So they just started from the left side, or right side, and went to the left. Whenever I did mine, I just did mine the other way. I just kind of like, I guess I like working left to right. So let's look and see how this works out for them. 6 times 2, or well, 4 times X. Again, I like to keep my extremes on the left and my means on the right. We've talked about extremes and means, where those come from. So 6 times 2, I would have put it on the left, but I guess they want the x over here. And 4 times x is 4x. So we end up with 4x equals 12, which is the same thing I had right over here. Divide both sides by 4, and we get x equals 3, so the length of QR is 3 centimeters. Let's go ahead and work on this one down here in the check it out. So find the value of x in the diagram. And we have AB, so let's take AB, and it matches up with WX. So here's WX up here. So I know that 5 is to 7. So let's set that up. 5 is to 7 as, now we started here on the left, so let's stay on the left. BC, the second and the third, so that must be XY it matches up with. And indeed, here it is there. So we have 2 is to X, as 2 is to X. Cross multiply, 5 times x is 5x, and 7 times 2 is 14. Divide both sides by 14, x equals 14 over 5. If you wanted to simplify that, we could say x equals, 5 will go into 14 twice with the remainder of 4, and not 10. Why I'm doing 10, I don't know. Denominator stays the same, 2 and 4/5, so not quite 3, right? Look at the next one. You can solve a proportion involving similar triangles to find the length that is not easily measured, such as this tall totem pole. We're not sure how tall it is, but we're going to use some indirect measurement to find it out. This method of measurement is called indirect measurement. If two objects form right angles with the ground, you can apply indirect measurement using their shadows. Helpful hint, the height of a 90-foot I guess we should read this after we get the solution. So we'll go ahead and come back to that after the solution, right? So a totem pole casts a shadow 45 feet long at the same time that a 6-foot man casts a shadow that is 3 foot long. Write and solve a proportion to find the height of the totem pole. Well, both the man and the totem pole form right angles with the ground, and their shadows are cast at the same angle. You can form two similar right triangles. And I'm going to do some overwrite here. Let's look at this. We'll look at the center of the triangle, or the center of the totem pole here, out to the tip of its shadow, and then from the base of the totem pole up through its height. And then we have the length of the man. We'll go the center of the man to the end of his shadow, and then right up through the man through his height here. Now, suppose the sun is up over here someplace, casting this shadow down this way, right? Well, the sun is striking both the totem pole and the man at the same angle. So we know that this angle right up at the height of the totem pole and the angle at the height of the man, we know that these two angles here are congruent. Let's go ahead and put that other line in there, right there along the shadow there. And we'll also go from the top of the man's head down to there. So we know that, and I'm going to change colors here. Let's go to black, I guess. We know that this angle right here, and this angle, well, I should be drawing with an arc. This angle here and this angle here, we know that those are congruent with one another. Again, congruent means the same size or the same measurement. We also know that they're at right angles to the ground, so we know that we have this angle and this angle here are also congruent, and that's not a very good color. Let's try it. Does green show up better? Yeah, I think it does. So we know that those are right angles, and again, the sun striking there and there, so we know those angles are congruent. Since we have two congruent angles out of the three, and we know that the interior angles of all triangles equal 180 degrees, then we know that this angle right here at the end of their shadow is also congruent. So we know that all three angles are congruent. The angle at the base of the totem pole and the base of the man are both right angles. The angle at the top of the totem pole and the angle at the top of the man, those are both congruent because the sun is striking both of them at the same angle. And since those two angles are congruent, then that means the third angle is congruent as well. Therefore, we know that these indeed are two similar triangles. So with that said, I'm going to go ahead and erase all this overwrite I have here, clean that up a little bit, and let's go ahead and look at this. So we're going to go ahead and set up a proportion that says the height of the man is to the height of the pole as the length of the man's shadow is to the pole's shadow. So let's go ahead and start plugging some of those numbers in. Well, the height of the man is 6 foot, so we have a 6 here. The height of the totem pole is the unknown value, so that's x. The man's shadow is 3 feet, so we'll plug that in there. And the pole shadow is 45 feet, and we'll plug that in here. Let's use some cross products. 6 times 45, again, they're putting it on the right instead of the left, but 6 times 45 is 270. And 3 times x is 3x. Now let's divide both sides by 3. The 3's will cancel each other, leaving me with just x. 270 divided by 3 is 90. Therefore, the totem pole is 90 feet tall. So back over here to helpful hint that we started to read at the beginning and then realized maybe we should read it after we get done. So the height of 90 feet seems reasonable for a totem pole. If you got 900 feet or 9,000 feet, maybe you got an extra zero in there somewhere, then that would not be reasonable, and you should check your work. So always make sure, especially with word problems, that your answers make sense. If every dimension of a figure is multiplied by the same number, the result is a similar figure. The multiplier is called a scale factor. So example 3, changing dimensions. Every dimension of a 2 by 4 rectangle, here we see the 2 by 4 rectangle, rectangle A, is multiplied by 1.5 to form a similar triangle. So 2 times 1.5 is 3, and 4 times 1.5 is 6. So we multiply both the length and the width by a scale factor of 1.5 to get a 6 by 3 triangle. Again, we know that all the angles are indeed congruent with one another. It's a rectangle, so we know they're all 90 degrees on A, and they're all 90 degrees on B. And since we multiplied by a scale factor, we know that the proportion of the sides are proportionate as well. So we know indeed figure A is similar to figure B. How is the ratio of the perimeters related to the ratio of the corresponding sides? And how is the ratio of the areas related to the ratio of the corresponding sides? So let's go ahead and set this table up here. First we have the formula for perimeter. Perimeter equals 2 times the length plus 2 times the width. And area is equal to length times width. So we'll just plug those in. First for rectangle A, we would plug in the sides 2 and 4, do the math, and we would get 12. So rectangle A has a perimeter of 12, and rectangle A has an area. By plugging in the 4 and the 2, we see it's an area of 8. For rectangle B, we're going to plug in 6 and 3, do the math, we get a perimeter of 18. And if we plug in 6 and 3 for the area formula, we would get 18. Interesting. Perimeter, area for B are exactly the same. So let's go ahead and set up a proportion for the sides. One, we have 4 is to 6. We have this here as 2 is to 3. 2 is to 3. Set that up. And we would get 2/3. Now the perimeter of A is 12. And the perimeter of B is 8. So we're going to set that up as 12 over 8. And notice that 12 over 8 simplifies to 2/3, right? We're going to divide both sides by 6. 12 divided by 6 is 2. 18 divided by 6 is 3, so that simplifies down to 2/3. So notice that the ratio of the perimeters is the same as the ratio of the sides. Next, let's look at area. Area for rectangle A was 8, so we'll put that in here. The area for rectangle B is 18, so 8 is to 18. And this will simplify down to 4 over 9. Divide them both by, 2, right? We get 4 over 9. And if we could get to 2/3 somehow, indeed we can. 4 is a perfect square, 9 is a perfect square. So we could rewrite this 4 over 9 as 2/3 squared, because we would apply this exponent to the numerator and the denominator. 2 squared is 4, 3 squared is 9, so 2/3 squared is equivalent to 4/9. So we get them all down to 2/3, right? 2/3, 2/3, 2/3, except for area. It's squared. Now, what do we know about perimeter? Perimeter we know is the distance around the outside. We're actually talking about length. Length has only one dimension, so technically this is 2/3 to the first power. Kind of messy writing there, but you can see how it's to the first power because it's just one dimension, length. But with area, we're talking about length and width, right? So we have two dimensions. Notice that we end up with a 2 for the exponent. So the ratio of the perimeters is equal to the ratio of the corresponding sides, and the ratio of the area is the square of the ratio of the corresponding sides. Also, helpful hint, a scale factor between 0 and 1 reduces a figure, making it smaller, and a scale factor greater than 1 enlarges it. All right, let's take a look and see what about volume. What happens whenever we start talking about volume? Because see, we have a formula here for volume. So apparently we've talked about the perimeter, which is just one dimension, length. We talked about area, which is two dimensions, length and width. And now we're going to talk about volume, which has three dimensions, length, width, and height. So every dimension of a cylinder with a radius of 4 centimeters, see the 4 centimeters here for the radius, and a height of 6 centimeters, here we have the 6 centimeters, is multiplied by 1/2 to form a similar cylinder. How is the ratio of the volumes related to the ratio of the corresponding dimensions? So 4 times 1/2, that is another way of saying that is 1/2 of 4 is 2, and 1/2 of 6 is 3. So we look at this first. Let's plug in cylinder A and cylinder B's numbers here, or values for the formula for volume. So volume is pi r squared times height. So we have pi 4 squared times 6, and we end up at 96 pi. For cylinder B, we're going to plug in the 2 and the 3, right? 2 for the radius, 3 for the height, and we work that out to be 12 pi. So let's go ahead and look at the radii. 4 over 2, right? 4 is to 2. And this simplifies down to 2 is to 1, and we get 2. What about the heights? 6 is to 3. 6 is to 3. Well, we can simplify that down to 2 over 1, and 2 over 1 is 2. So we end up with 2 again. Now for the volumes, we get 96 pi and 12 pi. So 96 pi to 12 pi. 96 and 12 will simplify to 8 over 1. Divide 96 by 12, we get 8. 12 divided by 12 is 1. And just in case you're wondering what happens to the pi, pi's cancel each other out. So in this case, we end up with 8 over 1. And any number over 1 is equal to itself, so we get just 8. And 8 is a perfect cube. We could rewrite 8 as 2 to the third. Now notice this time we end up with all the same number, 2, 2, and 2, except we have 2 to the third. And this is because volume is dealing with length, width, and height. So we have 3 dimensions for volume, so we end up with a 3 for the exponent. So the ratio of the volumes is the cube of the ratio of the corresponding dimensions. That brings us to our guided practice. So let's see. Let's do 3 for the sake of time. Kind of a long video so far. So we have RV. So R and V, right? So we know that RV is 2 and the first and the last, WZ. So we know that 8 is 2. That's RV. And WZ is 4. 8 is to 4 as, and then the other one we have is RS, which is the first 2. So RS is 2, and the first 2 is WX. WX. So what is WX? Well, first, what is RS? RS is the unknown X, and WX is a 5. So 8 times 5 is 40, and 4 times X is 4X. Divide both sides by 4, and we would get 10 equals X. So in this case, X equals 10. Here we have Roger's shadow is 5 feet tall and cast a shadow 3.5 feet long. At the same time, the flagpole outside his school cast a shadow of 14 feet long. Write and solve a proportion to find the height of the flagpole. So this, again, seems like this flagpole question shows up in every math textbook. It actually entertains me. It seems like flagpoles must be the hardest thing to measure, and we have to use indirect measurement for it. So at any rate, if we kind of sketch out a picture here, and we'll go ahead and let's do that for the flagpole. We'll do this for the man. Many times it's good to draw a picture if need be. And the Roger is 5 feet tall, and he has a shadow 3.5. And the flagpole outside of school casts a shadow 14, and we don't know how tall the flagpole is. So height of the flagpole is to the man, height of the man, x is to 5, as the shadow of the flagpole, 14, is to the shadow of the man, 3.5. So we would do cross products. We'd have 3.5. X is equal to 50. And then divide both sides by 3.5. And 50 divided by 3.5. Let's see, what's that come up to? 50 divided by 3.5 equals, oh, that's a nice unfriendly number, 14. We'll go 2 decimal places, 0.29. 0.29. It's actually 285, but I just rounded up to 9. So it would be about 14.9. And then a rectangle has a length of 12 feet. Let me do some erasing here, get rid of all this. And I think I need to move my picture there just a little bit so we can see all of it. And a rectangle has a length of 12 feet by 12 feet and a width of 8 feet. So let's go ahead and we'll draw that out. 12 feet by 8 feet. And I get that other line there, but that's okay. 12 by 8. And every dimension of the rectangle is multiplied by 3/4 to form a similar triangle. So the scale factor is less than 1, so it's going to get smaller, right? So we're going to end up with a smaller triangle here. And we need to know what these dimensions are. So scale factor, 12 times 4, 12 times, not 4, but 3/4, 3 over 4. 4 divided by 4 is 1. That's 3. So this is going to equal 9. So this side is going to become 9. And then if we multiply 8 times 3/4, 4 divided by 4 is 1. 8 divided by 4 is 2. 2 times 3 is 6 over 1 equals 6. So this side over here is 6. All right. Let me go ahead and erase this over here so I've got some more room to write. And the question is, how is the ratio of the areas related to the corresponding sides? So let's go ahead and look at this here. I have 12 is to 9. So 12 is to 9. And we can divide them both by 3, right? And we get 4 is to 3. Interesting. That's like the reciprocal of the scale factor that we multiplied by. And remember, it worked that way in our example during the text as well. So the ratio of the sides is 4 to 3. We could also see that with the 8 is to 6. Divide them both by 2, we would again get 4 is to 3. However, what about the area? 12 times 8 is 96. And 6 times 9 is 54. So what about 96 is to 54? Now, I believe that we could simplify this down to 16 over 9. And we're going to do that by dividing by 6. 96 divided by 6 is 16. 54 divided by 6 is 9. So we can simplify 96 over 54 is equal to 16 over 9. But 16 and 9 are both perfect squares, right? 16 is the same as 4 times 4, and 9 is the same as 3 times 3. But remember, we need to square both those, so we would have 4/3 squared. So the relationship between the ratio of the area is the same as the ratio of the sides, 4/3, only it's squared. Because remember, it's going to be, in this case, it's going to be, what's the word I'm looking for? 2 dimensions, length and width. So we're going to end up with 2 dimensions, so our exponent's 2. I'm sitting here thinking, what if we had an example with area? we would have had to have a height of it as well. In this case, we could look at that as what if they were cubes? What if we had something like this? And we had, that's not very good drawing there. Let me back up a little bit. So if I had I'm going to get myself in trouble here. I just know I am, because I can't draw either. So, not very good. Kind of penciling it, trying to work that in. This way, this way. So what if we had 12 by 8, and then this side here, we would have to go, well, let's just say it's a height of 4. Yeah, we could go with that, right? And then we would end up with another cube that was, in this case, it's actually not a cube, it'd be a rectangular prism. Almost looks like a stick of butter, don't it? In this case, we have 9 by 6, and then 4 times 3/4. To get that height, we'd have to go 4 times 3 over 4. The 4's cancel each other. Okay, and it would be 3 tall. And so we would end up with, in this case, we just end up with 4/3. And, this is a good way to explain how to work it backwards, right? I want to figure out the volume of this. I could just go 4/3 and realize that this is going to be cubed. And so then I could do 4 to the 3rd over 3 to the 3rd. And we'd end up with, looks like, 9? Right? But at any rate. So if it were a volume, we would have to the 3rd power. Spent a lot of time. Maybe I should have messed with that. But so that is the completion of my presentation for Algebra 1, Chapter 2, Lesson 8, Applications of Proportions. Thank you.